Okay, the next topic is the finite well. Well, it's finite, not infinite. So the finite well looks like this. You have a potential, and the potential is 0 if x is between 0 and L, and it is u naught. Instead of being infinite, it's now u naught otherwise. Okay, we can plot this potential as follows. Here's u, here's x, this is 0, this is L, and that's the potential. This is, this height is u naught. And our goal is to find solutions where the total energy of the particle is less than the height of the well. Less than the height of the well. And what happens is, imagine you have a, let me make them, instead of the walls being square, let's say I have a roller coaster. Okay? A roller coaster here, and the potential energy from here to here is u naught. This is the potential energy. And let's say I have a cart, and it starts at rest, and it has an energy E. What would the cart do?
Roll back and forth.
Roll back and forth. The state's friction. Roll back and forth. So the cart will get all the way here and then come back, right? Those are the turning points. Can the cart be here? Or can the cart eventually escape and get here?
No.
No. In here, it's actually going to be different. The particle can be in the well, and it has less energy than the height of the well, and there is a chance that the particle will tunnel through and be outside of the well. And in fact, we're going to, when we do the barrier, that's when we would have, would be more appropriate to talk about that. In this case, we're just looking for the bound states, the bound state energies. So we're interested, what are the energy levels? Yeah, sorry, for that one, forget it. When we get to the barrier, I was thinking ahead of myself. So let's say we're assuming this, E is less than u naught, okay? That's the first assumption. And we're not going to solve the problem completely. We will get through a good bit of it, and then we'll just quote the answer. So for x inside the well, the potential is 0, right? The potential is 0. So that means the Schrodinger equation is going to be minus h bar squared over 2m, second derivative of psi dx squared is equal to e prime psi, right? Because u is 0. That means the second derivative of psi, just exactly what we did earlier. Second derivative of psi dx squared is equal to minus 2m e over h bar times psi, which is equal to minus k squared times psi, where k again is 2m e over h bar. Okay, over h bar. That's it. Now the solution to this, or psi is equal to a times the sine of kx plus b times the cosine of kx. Now notice here, we're not going to be able to throw away a nor b, because the wave function here, outside, is not gonna be zero. The wave function outside is not going to be zero. Why? Because the potential is not infinite. Remember earlier, why did we say psi had to be zero? Because we have infinity times something. If this is not zero, then the left side will be infinite, and the right side, psi, is finite. But here, u is finite, and so psi could be non-zero. And in fact, it is. So this is this wave function here applies for 0 to x to L. Let's do the one for x greater than x. Let's do the one for x less than L. X less than 0, sorry. X less than 0. Actually, before I even x less than 0 and x less than 0 and x greater than L. Here is how the equation looks like. We'll have minus h bar squared over 2m, second derivative of psi with respect to theta with respect to x, plus u times psi is equal to e times psi. And that means minus h bar squared over 2m, second derivative of psi with respect to x is equal to e minus u times psi. Now again, multiply both sides by 2m and divide by negative h bar squared, and we get second derivative psi with respect to x is equal to minus 2m u minus e. Actually, since I do u minus e, I will just do this. Erase the minus sign over h bar squared times psi. Now, do you agree that since we're assuming e is less than u naught, I forgot to write u naught here, then u naught minus e is going to be a number that is positive, right? U naught is going to be a positive quantity because u naught is greater than e. Okay. And we're going to call this kappa squared times psi, where kappa, I know the book uses the letter kappa, so I'm going to use kappa just like that. It looks like K, but it's not K. That's the wave function, or with this kappa. And now we need to solve that equation to see what we get. So let me rewrite that equation. Second derivative psi with respect to x is equal to kappa squared times psi. Solution to this would be, can someone tell me? Second derivative with respect to x give you the wave function, the same function back, but times k squared or kappa squared instead of negative sign. There is no negative sign. What would the solution be? It would be actually exponentials in this case. Let me write it and see. I used a and b, so c e to the kappa x plus d e to the minus kappa times x. Let's think about it. Take the derivative twice. Derivative of exponential gives you exponential back. But every time you take a derivative, kappa comes down, so that's kappa squared. Same thing here, but you get the negative kappa twice. Minus times minus is plus, so you just get kappa squared. So either one of these satisfies that differential equation. Now, let's focus on x less than 0. For x less than 0, when x goes to minus infinity, remember, the wave function needs to go to 0 in order for it to be normalizable, in order for the integral to be to converge. what do I need from the wave function? What do I need the wave function to have? What should the wave function be when x goes to minus infinity? Think from, let's say, Calc 2. You have a series for it to converge. The first test to make sure that it's not divergent. What should the sequence of numbers a1, a2, an? What should happen to an as n goes to infinity? The n term should be getting smaller, right?
For it to converge?
Yeah, right. So if it doesn't get smaller, if it doesn't go to 0, then it's divergent. So the very first thing, the wave function needs to go to 0 as x goes to plus or minus infinity. Right? So when x goes to minus infinity, e to the minus infinity, is that 0? Yes. Right? It will approach 0. How about here? E to the minus infinity.
Infinity.
That will grow without bounds, right? So what we need for this one, psi, is just c e to the kappa x. That's the only one that's acceptable. This one is not physically acceptable. For x greater than L, the opposite happens. So when x goes to infinity, I need psi to go to 0. So which term should I keep? This is this one, right? Because e to the minus positive becomes minus infinity. But this one will not be acceptable. So that means this. We get psi is e to the kappa d e to the minus kappa times x. Here's a summary of what the wave function is. And then e to the minus kappa x for x greater than n. That's the wave function. And that's where we're going to, I will just tell you what you would do and then how to continue, but I will stop right here. I'm not going to go any further from this, but what you will do is this, or what one would do to get the full picture. It will take a lot more than, it will take a little longer than this. What you have to do is require the wave function to be continuous at the boundaries. So you match, you say at 0, you get c e to the 0, that's c, right? At 0, the wave function needs to be continuous. So we get c is equal to, this one at 0, so you get c will equal to b, because sine of 0 is 0, b times the cosine of 0 is 1, so you get b must equal to c, because of that boundary condition at 0. The next boundary condition is this and this must match when x is equal to L. You plug in L and then it must match. The next thing that needs to match also is the derivative. The derivative needs to be continuous because after all you have to take the second derivative. So the first derivative generally needs to be continuous, and so you say the derivative at 0 needs to be also continuous. So you take derivative of this at 0 and match the terms. And then derivative of this at 0 and then you match the terms. And then the last thing you need to do is require the wave function to be normalized. And then you'll be done. And then after you do all that, what happens is you will get the transcendental equation, which means you can't isolate the energies by themselves. It will be some function equals to something with a tangent, and then you have to solve it numerically. So, that's what happens. Most problems in quantum mechanics are not solvable exactly. You have to numerically solve them. So, doing these numerical solutions, you will get the following. Here are the energy levels. First of all, the infinite square well, infinitely deep well, let me write it here. The E1 for the infinitely deep well. right? E1 for the infinitely deep well is equal to H, what was it? H over 8m times L squared, right?
H squared.
H squared. Thank you. Where should I point to it? Where is it at? I can't find it. Okay, over there, right? Yeah, H squared over 8ml squared. Yeah. So that's the energy level for the infinitely deep well, right? How do the energies of this finite well compare? Well, there are, I would quote the first three. It depends on the depth of the well also, but the first three are this. E1, this is for the finite well, E1 is equal to 0.625 times the energy of the first energy level of the infinitely deep well. E2 is equal to 2.43, the first energy level of the infinitely deep well, and then E3 equals to 5.09 of E1 of the infinitely deep well. And we would go through the derivation, but we need like 3 or 4 more weeks in the semester. There are a few theorems that you have to prove about some properties, but this is the summary of what we have. Okay? Let me again ask if there are any questions on this one. Again, we didn't derive these. It's in the book. You can check, look it up, or just copy it. So, yes.
What do we do with this? What did we just solve from?
These are the energy levels in a finite well.
But we're using an infinitely.
So they are related to the infinitely deep well by these. So let's do an example. Maybe when we plug in some numbers, it will make more sense, right? So let's say, here's the example. Let's wasted space here. Okay. An electron is trapped in a finite square well. Example. An electron is trapped in a finite well, square well. Of width L equals to 0.5 nanometers. So A, find E1 of the infinitely deep well, and then B, find E1, E2, and E3. These are for the finite one, yeah, and this one is the infinitely deep well. So for the infinitely deep well, we have E1 for H squared over 8 times L squared. Now we don't have to do any calculation for this. We did it earlier. Here it is. It's the same width. So we will just recycle our answer from earlier.
Nice.
Yeah, so it's going to be 1.5 EVs. Okay, good. B. Now for the finite well, E1 is going to be here. It's 0.625 times that of the deep, of the infinitely deep well. It's going to be 0.625 times 1.5 EVs, and that turns out to be 0.94. E2, well, that's 2.43 times 1.5, and that gives 3.6 EVs. E4 is going to be 5.09.
E3. E3 or E4?
E3, thank you. E3. It's gonna be 5.09, 4.5, thank you. And then that turns out to be 7.6 EVs. Now, there are E4 and E5 and so on. Depends on how deep the well is. Depends on what U naught is. So if the well, let's say the depth, for example, if E3 is 7.6, if the depth is, let's say 8 or 9, that's okay, because you will have, all of them will fit within the well. But let's say if the depth is only 5 EVs, suppose U naught is 5 EVs, how many energy levels can I have? Just 2, E1 and E2, right? Because those are the ones that are bound, or the ones that fit within the depth. Because remember, E must be less than U naught, right? E must be less than U naught.
Is it possible for none to fit? What does that mean?
For none to fit?
Yeah.
So if good question, let's say the well is very shallow. If it's extremely shallow, then there would be only one energy level. No matter how shallow it is, there will still be one bound state.
The first one, whatever it is.
The first one, whatever it is. Yes. Yeah. I believe it's bound state, I forget what the number was. I don't have it top of my head, but there is a certain number, yeah. But yeah, no matter how shallow the well is, there is always a bound state. It can be shallow. Yeah.
Cool.
Yeah. So that's the finite. Yes?
What's a well?
Oh, what is a well? So these are terms that we borrow from everyday life. And so in here, it's just a mathematical function, as far as we're concerned, a mathematical function that is 0 and then it has a certain height. So we borrow this, imagine you're inside a well and you want to climb the walls to get out. Yeah, so the height of the well will be, huh? That is U naught, yes. Yeah, so let's say this classroom, the height is 4 meters.
So
Yeah.
in this case, U naught is our highest energy level?
U naught is,
Like if we're thinking about it as a well.
yes and no. In classical, yes, the highest energy level you can attain is that. But in quantum, the energy levels are discrete. It may or may not match. So, for example, as I mentioned earlier, let's say if this well, let's say U naught is 9 EVs. So here is U naught. Let's say it is 9 EVs. This is U naught. So
Max potential?
yeah, this is the maximum. Yeah. So E1 will be somewhere here, right? E2 would be here. E3 is here. E4 will exceed. So the only bound states where the electron is trapped in this well are these first 3. If you have more, then the electron will be outside of the well.
So U naught is the max that it could be?
U naught is,
It could be, like let's say E3 could equal U naught?
it could, yeah, it could be up to that. Yeah, it could I guess, match to it, yes. It's hard to match it, but yeah. Again, these values here, though, they're not exact, they're approximations. The next one is a barrier. So what is a barrier? So it's the reverse of a well. So let's do the next one. It's called the potential barrier.